All righty. I believe that it is time for us to start. I'd like to welcome you all to the 10th in a series of Zoom lectures that are sponsored by Congregation KINS. And by now, as you know, they involve STEM topics: science, technology, engineering, mathematics, medicine. And the speaker who was originally scheduled for today, Dr. Jonathan Greer, unfortunately came down with COVID, and complicating that is he completely lost his voice. And so I am going to be his substitute for today. His presentations have been pushed back until December, and you will receive timely notification of that. The topic today is the periodic table of the elements and the master chemist. Unfortunately, Rabbis Matanki and Bressler were unavailable today to introduce me, so I have the dubious honor of introducing myself. The advantage to that, of course, is that I can do it in 15 seconds instead of 1 or 2 minutes that they would have done. So very briefly, I grew up in Charleston, South Carolina, had a multi-year Hebrew school education there, went to college in Charleston with a BS in chemistry, pursued and earned a PhD degree in radiopharmaceutical chemistry. That's the use of radioactive drugs for diagnosis and therapy. Currently, I'm a professor in the nuclear medicine department at Loyola University Medical Center, located in West suburban Maywood. And I just started this past July, my 38th year there. I've had 45 years of teaching experience, and my hobbies are photography, woodworking, bike riding, and reading. I'm going to encourage you to ask questions. If you have anything that you would like to know, please feel free to unmute yourself. And now I am going to share the screen with you. And we're going to go ahead and get started. The title today is The Periodic Table of the Elements and the Master Chemist. The Master Chemist, of course, being not me, but Hashem. And the Periodic Table of the Elements part of this is going to take no more than 5 minutes. There are certain assumptions that we've had to make, one of which is that Hashem created all the elements when he created the earth and everything on it, and the oceans and everything in them, and all the heavenly bodies, the sun, the moon, the stars, and other heavenly bodies. Because of the modern day technology available, there are now many chemical and physical techniques so that we can determine pretty easily the chemical composition of anything. And in addition to that, because of radiometric techniques, I'm sure you've all heard of radiocarbon dating. That only goes back, though, perhaps 20, 30, 40,000 years. There are other techniques similar to that that can go back for millions or even billions of years. And because we are now looking at the end products of all that radioactive decay, we can project backwards in time and know that those isotopes had to be there in the first place at the time of creation of the world. Every day we thank Hashem for giving us all the knowledge that we have, not just scientific, but all of the knowledge. Every day we say, Atah chonei l'olam das. We thank Hashem for giving us knowledge, for understanding, for discernment, for prudence in what we do with this wonderful knowledge that he has given to us. One of the things that you probably have all observed is that Hashem has kept his scientific secrets in a secret compartment somewhere, and he has released them relatively slowly over the centuries to mankind. I would have to say, though, in the last 100 years, he has opened up those secrets a lot more than in the past. This is just the lead in into the bit about the periodic table. In the Jewish year 5630, which was the secular year of 1869, Hashem gave a Russian Jew, Dmitry Mendeleev, a lot of insight. He took all of the known knowledge about all of the elements and put them in a tabular form. And when he did that, he observed that certain vertical groups in this tabular form had very similar properties. When I first started preparing this, I was thinking about how many elements could Mendeleev have already known about back in 1869. And my prediction probably would have been 25 or 30 elements. And as you'll see on the next slide, that is not at all the case. It's more like 60 or 65 elements that were known over 150 years ago. Today, we know that there are actually over 110 elements. There are 2,900 known nuclides, most of which are radioactive and most of which never occur in nature. And to identify them, we have to synthesize them, characterize them, and learn what we can about them. So this is the list of all the elements that were known before the periodic table was first developed. And the ladies in the audience will be very happy to know that silver and gold were some of the very first ones in the early history of mankind. And from 1669 all the way to 1863, you are looking at the 60 different elements. These are elements that were discovered after Mendeleev did his early work. And most of these in the far right-hand column are radioactive, almost every single one of them radioactive. So we're now looking at over 110 elements altogether. Here's a photograph of our good friend Mendeleev. And what he did was he arranged a table based on the atomic masses of all of the known elements. That turned out to be a pretty good way to do it, but unfortunately, as we'll see shortly, not the very best way to do it. But what he did notice is that in the vertical columns in his table, again, those seem to have similar chemical properties. I want to show you something that very few people on this earth have ever seen. This is Mendeleev's first draft of the periodic table in his own handwriting. It was not easy to find, but as you know, the internet is the source of all knowledge. And if you look hard enough, you can find almost anything there. 2 years later, at the annual meeting of the Russian Chemical Society, this is a periodic table that he published. And if you look here at the vertical groups, you can see, for example, lithium, sodium fits in here, potassium, rubidium, cesium, all of those have very similar chemical properties. Back in the early 1890s, Sir William Ramsay, who was a British chemist, predicted and then discovered several examples of what we today call noble gases. Back when I was in high school, you probably, and if you, maybe when you took chemistry, you heard about the inert gases. Not any longer. They are now known to undergo reactions under some pretty violent conditions, but they do form compounds. So they are now referred to as the noble gases. And Ramsay expanded on Mendeleev's periodic table and found a good place to put all these noble gases. And here's one of the real geniuses of all chemistry. Henry Moseley was also a British subject, and he discovered that instead of arranging that table by atomic mass, he did it by the number of protons. And then that actually left spaces in the periodic table where he knew we had to find those elements. And here's one of the amazing things. This man, Henry Moseley, accomplished everything at a very, very young age because he unfortunately died at the ripe old age of 29. Back when I was in high school, this is the bare bones periodic table of the elements. And you all, if you've taken chemistry, I'm sure you've seen this or a more modern example of it. And you'll note down here at the very bottom that we're up to element 101. And there are two changes from this one to the modern one. Down on the bottom, you'll notice element number 99 is E, named after Einstein, and MV, named after Mendeleevium. And now this is the more modern 2020 version of the periodic table. it's color coded. The alkali metals, the alkaline earth metals, the transition metals, the non-metals, the noble gases. And look what has happened to the names of those two. You'll recall they were E and MV, not anymore. ES is now Einsteinium, and let me get back to it. That's getting my way here. And MD is now Mendelevium. So this is the periodic table that all chemists have readily available to them. Now, some of the assumptions I want to make are listed on this slide. Number one, other than me, there probably are not any other professional chemists participating today. Point number two, not everyone has even ever had a chemistry course. And number three, of those of us who have studied chemistry, it might just be a distant memory. And so I don't think showing complex molecular formulas is going to have very much value today in understanding how Hashem is the master chemist in our world. So the game plan here is that I want to explain to you some things that we simply take for granted on a daily basis. And they are all chemistry based. And as the slide indicates, they represent what I like to refer to as a super intelligent design. And what this should do is to give you an understanding of how Hashem runs the world. And there are miracles that are taking place in our lives, in our bodies, every second, minute, hour, day, week, month, year, and so on. We just take them for granted. We don't even give them a thought, but there's some masterful chemistry going on here in the background. So the remainder of this is going to be divided into three separate areas. One is going to be chemistry as it relates to food. The second will be chemistry and how our bodies function with certain chemicals. And these two, by the way, 1 and 2, are really pretty inseparable because food and our bodies simply go together. So it's pretty hard to segregate number 1 from number 2. And also some interesting chemistry things that go on in our everyday lives. Now, the very first topic is chemistry and food. And there is something that we need to discuss in detail before we can even proceed from this. And that is may not sound too interesting at first, but that is the fascinating topic of dirt. You can see on the left some rich Chicago soil that I dug up in my backyard yesterday and took a picture of. And here is a picture of some Georgia red clay. And they obviously don't look at all alike at first glance. But here's what we have learned. Well, on the next slide, I'll show what we've learned. But this slide is going to answer the question of who is in charge of this world. You can just imagine this conversation between God and a scientist. The scientist says to God, I can create essentially anything. I can make any fruit or vegetable. Just tell me what you would like for me to make. And God says, okay, let's see you make a pepper with red, green, and purple stripes. And the scientist says, no problem. I'm a genius at genetics and chemistry, and that's going to be an easy project. Let me go get my shovel. And then God says, not so fast. Go get your own dirt. It's pretty clear who's in charge here. So if you look at the last sentence on this page, human and animal life would be impossible without dirt or soil or earth or whatever you would like to call it. And so we need to have a brief discussion of these topics as well as sand and rocks. And just keep in mind, we take for granted the presence of soil. We want to plant our tomato plants. We go in the backyard, dig a hole, plant our seeds, plant our plants, and off they grow. And so we don't really pay much attention to the chemical composition of soil. No one does, even most chemists don't. But what if there was only sand, beautiful white beach sand, or rocks, but no dirt? We would not be alive today. That beautiful white beach sand is pure silicon dioxide. If you melt it down under very high temperature, you make glass. That's all the glass is molten silicon dioxide that's been allowed to cool. And what's conspicuously absent in that beautiful beach sand is that there are no nutrients that support life. for plants or animals. And so the master chemist Hashem has ensured that all the elements that we need to maintain our good health and our life are present in a water soluble form in all the different kinds of dirts and soils that there are. And they're in the correct proportion. If you've ever bought a bag of fertilizer from Home Depot for your garden, you'll see on it 10, 10, 10. Look on the very bottom line. Plants need 10% nitrogen, 10% phosphorus, 10% potassium. We humans need those same things, but in different proportions. But everything that we need to maintain health and life is in the soil. And so take a look at why we don't want our earth covered with nothing but beach sand. What's there? Silicon dioxide. That's it. But look what's in soil. And this is not even a totally comprehensive list. There's calcium, there's potassium, there's iron, zinc, magnesium, chlorine, phosphorus, misspelled. That's just a photograph of a table. Sodium, sulfur, and many other elements that are necessary to support life. So without soil, again, we simply would not be here. So there really is no one formula that represents the chemical composition of soil. No matter where you are in this world, the soil composition is different. It's not just different from my back to your backyard, but it's different from Illinois to Indiana to Georgia to California to Russia or any other place in the world. The important thing to note, however, is that all soil, regardless of the chemical composition, has everything that we need to support human life. Now, let's take a few examples of food-related chemicals that have a huge impact on our life. One of the first ones I want to mention is vitamin C. We don't think too much about vitamin C. Everyone probably knows that it's present in essentially all fruits and vegetables. But here's why Hashem had the brilliance to put it in all fruits and vegetables. Almost every animal on this planet, except for humans and our primate cousins, synthesizes vitamin C in their bodies. We humans cannot do that. And without a dietary source of vitamin C, we would have a very tough time surviving. But other animals don't need to eat all those fruits and vegetables. They make it on their own. And for the chemists in the crowd here, here's a little formula for ascorbic acid, which is vitamin C. And vitamin C is really a lot more important than we're even aware of typically, because it's necessary for everything listed on this slide. Repair and growth of body tissues, collagen formation, especially important for the absorption of iron. In fact, iron supplements actually often contain iron ascorbate, that's ascorbic acid, because that's the most easily absorbable form. It helps to maintain the immune system and all the other things that you note here, cartilage, bones, teeth. So it's a very important chemical. There are many other minerals that are present in our food, and life would be very difficult without them. That list is so long that to cover all of them would take days. So I've just selected a very few of them to give you some insight into the way that Hashem has set this world up from a chemical standpoint. Let's take a look at calcium, for example. Everyone knows that most of the calcium in our body is in our bones, and very little of it is actually flowing in our bloodstream. We can't live without it, but it doesn't take much in our bloodstream to keep us healthy. And it is by far the most common mineral that's in our body. Things that we all probably know about. It repairs bone and teeth, and helps nerves work, helps blood clot, muscle contraction. And here's something interesting. People who have very low calcium levels or very high calcium levels are very prone to having cardiac arrhythmias. So it's very important for us to keep that calcium at the right level in our blood pool all of the time. And here's one of the miracles, and this is where we're going to correlate the medical aspects with the scientific or the chemical aspects. It is truly a miracle that for people who are healthy, perhaps even out to age 80, for people who are healthy and don't have any catastrophic illnesses, the level of calcium in our body is constant for our entire lives. This graph shows you very, very small fluctuations over a period of perhaps 80 or 90 years. And in fact, many of those fluctuations are due more to levels of hydration in the body than anything else. And there are different hormones that are controlling our calcium level in the blood. There's parathyroid hormone and calcitonin and some other things that keep our calcium level averaging between 8 and 10 milligrams per deciliter over decades and decades. You're going to see the same graph again for a couple of other chemicals that we have in our body, where we're going to see the stability of those levels over a lifetime. Those of you who are interested in making sure you're getting enough calcium, here's the places to get it. Yogurt in particular is probably one of the best sources. All milk products, calcium fortified orange juice, salmon with the bones in it, and so on. And by the way, if anyone is interested in any of these dietary source charts later, if you contact me, I'll be glad to share them with you. Let's take a quick look at iron. We cannot live without iron, of course, because iron is in hemoglobin, and that is what transfers oxygen throughout our body and oxygenates every single cell. And one of the things that people may not be aware of, yes, we're all aware that carbon monoxide is dangerous, and in an enclosure, it can kill you pretty quickly. But the reason for that is that carbon monoxide has an affinity for hemoglobin that's over 210 times the affinity of oxygen for hemoglobin. And what that means is that if someone is in a car with the motor running in a garage, you might think, well, 21% of the air is oxygen. There's plenty of oxygen there. Why should I worry about leaving that car running? The problem is that carbon monoxide, it doesn't take very much to reach toxic levels because of that very high affinity. Again, what's very miraculous is that our hemoglobin levels, when we're in good health, are literally constant over a lifetime, again, assuming nothing catastrophic is going on. And the body is able to keep those levels at a very constant level, even when there are those small fluctuations due to either diet or level of hydration. Good sources of iron are listed here: liver and red meat, a different collection of beans and fortified cereals, and some other things. I don't want to dwell on that slide so much. Iodine is a very important mineral found in our foods, and it is very critical to have a good level of iodine in our diet. The average American consumes about 100 to 150 micrograms, not milligrams, but micrograms of iodine every day. That's all that we need to maintain thyroid health. And we're going to take a look at where iodine is in our diet. Mostly it's in foods that contain fish and sushi, and especially anything that has seaweed in it. Every time you eat sushi, you're eating seaweed. Also, most of the salt that we use at home and manufacturers use in food products contain iodized salt. So we're getting it every single day. Why is iodine so important? Iodine is used to make the several thyroid hormones. They are truly very complex chemical reactions, but to make the thyroid hormones, which control our metabolic rates and development of bones and brains, and especially during pregnancy and infancy. There are several, excuse me, there are several hormone levels. If you ever go to your doctor for a checkup, they might say, I want to check your thyroid hormone levels. What they typically check is T3 and T4 and TSH. T3 is triiodothyroxine. This is iodothyroxine. This is thyroid stimulating hormone. And again, what's miraculous is that for people in good health over decades, those levels are simply as stable as a rock. They fluctuate very little if you're in good health. Dietary source of iodine, dried seaweed. Take a look at this, almost 3,000 micrograms. That's almost 2,000% of the daily required value. So one of the best sources of iodine for us is sushi or anything containing seaweed. Fish, especially ocean fish. Lake fish don't have so much iodine, but ocean fish like salmon and tuna do have iodine, iodized salt, of course, potatoes, and many other food products. They're not, I didn't list everything, but many things have iodine in them. And we truly do not need that much to maintain thyroid health. But keep eating that sushi. Potassium, very important mineral that's always in our diet. Almost every fruit and vegetable has potassium in it. And it's very important for regulating our fluid balance, for keeping our blood pressure under control, for muscle contractions, people who have certain unexpected muscle contractions or leg cramps are sometimes low on potassium. So it's very important to keep your potassium level within normal limits, prevents against strokes, against kidney stones. And again, what's so miraculous is that our level of potassium is so carefully controlled that over a lifetime, it will typically fall in this range right here, 3.6 to 5.2 millimoles per liter over many decades. Now, it's interesting that everybody says, eat bananas. Bananas are good for you with potassium. And that is true because this is 358 milligrams, but that's only in a 3.5 ounce banana. So that means that the typical size banana, which might be 5 or 6 ounces, has more like 4 or 5 or 600 milligrams. But if you really want to pig out on potassium, here's what to do. Cook some beet greens. They have 900 milligrams from a 3 ounce portion. So lots and lots of sources of potassium. And you'll note here, sweet potatoes are good, and yams, which are technically different, have 50% more. Now, the daily requirement for potassium is about 3.5 grams. And if you ate 7.5 bananas in a day, you've picked up your daily requirement. You, of course, don't need to do that because almost everything contains some potassium. And one of the things that we know is that cardiac surgeons who need to stop the heart during surgery actually give the patient an overload of potassium, and that stops the heart from beating. And you might think, well, could that happen to me if I pig out on bananas? And the answer is no. For a healthy person, it would be impossible. No one could eat 400 bananas in a day, which is what it would be required to get a potassium level that could cause your heart to stop beating. So no one has to worry about that at all. The Harvard University website says you should eat a lot of chromophoric vegetables. Chromophoric means highly colored vegetables. They have all kinds of nutrients in them, phytochemicals, phytonutrients, protopectins, bioflavonoids, all kinds of antioxidants. And many of these chemicals are in foods that a lot of people don't care for too much, like cabbage and broccoli, cauliflower, Brussels sprouts, but they really are quite good for you. And it's interesting that people who eat lots and lots of fruits and vegetables, let's say 5 or 6 or 7 servings of fruits and vegetables per day, have significantly lower rates of both cancer and heart disease than people who don't do that. Secondly, let's take a little bit closer look at chemistry and our bodies. I found this interesting graphic here, and it describes the human body in 2 different ways. One is, what are the chemical elements of which we are composed? You can see on the left side, these are the ones that add up to about 98%. Our bodies are mostly oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. And then these are the more trace elements that total only a couple of percent. But there's another way of looking at the body, and that is, what are the chemical compositions, not the elemental compositions, but the chemical compositions. So we are mostly water, almost 2/3 water, 1/6 protein, 1/6 fat, small amount of carbohydrate, and the rest is minerals. And I put this in tabular form because it is kind of interesting to take a look at the last column here. We have in our bodies 100 pounds of oxygen, 27 pounds of carbon, 14 pounds of hydrogen, and lesser amounts of some of these other elements. I recall when I was in high school, our chemistry book had, it might have been tongue in cheek, I guess it was, the value of a human body. We, of course, all feel that the human body is invaluable, can't put a price on it. But if you took the chemical elements that are in the human body and sold it, 60 years ago, a human was worth about $1.35. Today, I think we're probably worth 10 or 15 times that much. Do you ever, we don't typically think about bile too much, that very dark brown liquid that is secreted by the gallbladder, and it goes directly into our intestines. Food which is mixed in our stomach picks up hydrochloric acid. So look at the mix that's in our intestines. We have hydrochloric acid and bile. You should be aware that that can digest and even the toughest piece of meat that you've ever seen in your life. But then you might be thinking, why doesn't it dissolve our stomach or our intestines? And so the master chemist has made sure that doesn't happen, because our digestive tract secretes a certain form of mucus that is pretty much totally impervious to that potent mixture that can destroy a piece of steak and convert it into a liquid. There's a lot in the news today about antibodies. Antibodies are very specific proteins that are formed by B cells. That's a type of white blood cell, and it's in response to a pathogen, or more particularly an antigen, something that causes a response. And our immune system creates these antibodies that are specific for the antigen. They bind together and the antigen is deactivated and rendered harmless. And the immunity for these antibodies can be conferred for months or years or even a lifetime. We all know that these childhood diseases, mumps, measles, chickenpox, once you're immunized, it's a lifetime immunity. Influenza, unfortunately, not so good. We have to have a flu shot every single year. And even with that, it's only typically 40 to 60% effective in preventing flu. And COVID-19, a lot of question marks there. We still don't know exactly what that protection is going to be. Some of the progress that's being made now on immunizations indicates that the immunity might be longer than we previously thought. It might be a lot longer than just months, but we'll have to wait and see. A couple of clever uses of these antibodies. We probably have heard on the television about convalescent plasma, where patients who have been exposed, for example, to COVID-19, donate after they've been healed, donate the plasma. It's antibody rich, and it is concentrated and given to patients who are seriously ill in the hospital. And it has reduced a lot of suffering and probably saved many lives. Here's another clever use of antibodies. Those of us in nuclear medicine are very familiar with what are referred to as diagnostic radionuclides. They're radioactive nuclei that are imageable outside of the body, similar in concept to X-rays, but they are emitted rather than being transmitted. And so we can bind these isotopes to specific antibodies and make the diagnoses for imaging for things like melanoma, prostate cancer, colorectal cancer, and many of the others. People often think, oh, radioactivity, that's going to be a very high radiation risk. In fact, the radiation risk is quite small. The radiation dose from a CAT scan, a CT scan, is a much higher local dose than any diagnostic radioactivity. We can also combine these antibodies with therapeutic radionuclides and treat patients. For example, we have a yttrium-90 anti-lymphoma antibody targeted to what is called the CD20 receptor on B-cell lymphoma. And that drug can actually put some people in remission, and in others cause significant tumor shrinkage and lengthening of life. If you had some basic knowledge of chemistry, and let's say you wanted to perform a bone scan, how would you approach this? You would say, okay, bones are primarily made out of this calcium phosphate. And you would say, let's find a good calcium isotope, or let's find a good phosphorus isotope and inject it and make a bone scan. Unfortunately, there are no good diagnostic calcium or phosphorus isotopes, but there is an element called technetium-99m, and we can bind technetium to these phosphate groups. And in fact, there are 3 phosphate drugs available today for diagnosis. And this slide will show you here a bone scan. This narrower scan on the left is a totally normal bone scan. You'll note perfect symmetry. There are no hot spots anywhere except here in the knees. And these are simply growth plates, which indicates this scan is done on a young person, probably a teenager. This scan on the right, however, this is a front and reverse view, anterior and posterior. And this is a patient who has very widely disseminated prostate cancer. And every one of these little black spots here is metastatic disease. You don't have to be a physician to look at this and say, that patient is in serious trouble. There's disease literally everywhere. Treatment of hypothyroidism. This is actually today very easy to treat. And the drug that is typically administered is called Synthroid. As that name implies, Synthroid is a synthetic thyroid hormone. In fact, it's identical to the T3 and T4 that your thyroid normally produces all on its own. But if your thyroid is not producing enough, you'll simply take Synthroid the rest of your life. Typically has never any adverse reactions. It's also interesting that hypothyroid patients tend to be female. Probably 80% of all of them are female. Just related to this Synthroid business, between 1945 and 1955, physicians used to irradiate the necks of children who had either tonsillitis or what is referred to as an enlarged thymus gland. That was actually considered a state-of-the-art therapy back then, about 70 years ago. And many, many people underwent those procedures. It was later learned, however, that the thymus gland is really large in children, but shrinks considerably during an adult. And there was never any reason to actually do this at all. The downside to it is that when the juvenile thyroid is irradiated later in life, 2 things are likely. One is the induction of thyroid cancer. And to make sure that that does not happen, what doctors do is give the patient Synthroid for the rest of their lives. That basically shuts down thyroid function completely. Your thyroid doesn't work. Therefore, the likelihood of induction of thyroid cancer is very close to 0. And so we have a very good way to treat those people who as children had that neck irradiation. There's some very interesting history here about development of medical things. 3,500 years ago, there was a papyrus that was found a lot more recently than that, that recommended using myrtle leaves to cure rheumatic pain. And the father of all doctors, Hippocrates, favored the juices from the poplar tree and the willow bark. Now we're going back thousands of years. And why did those relieve pain? We now know the reason because we're pretty good at chemistry. That is that all of those biological materials from the trees contain salicylic acid, which in fact is the primary ingredient in aspirin. Um, Today, the molecule has been slightly modified just to reduce the gastric irritation that can be caused in some people from taking aspirin. Here's interesting chemistry. Who would have thought 2,600 years ago that someone would have the intuition to take animal fat and heat it with wood ash, which contains lye or sodium hydroxide? Truly an amazing reaction took place. This is the only complex reaction I've gotten this whole presentation. But when lye reacts with animal fat, it creates two things, soap and glycerin. And this today is exactly how dial soap is made. This is a fat. It's got long chain fatty acids on a glycerin backbone. We end up with glycerol, which is the same as glycerin, and sodium palmitate. That's a 16 carbon chain. And today, the soap that we use is actually sodium stearate, which has an 18 carbon chain. That's a lot of really technical stuff. But the bottom line is that our master chemist made available centuries ago, millennia ago, soap. In the 1800s, Hashem let us in on a couple of chemical secrets. And one of those was polymer chemistry. In fact, a name that you'll all recognize, Charles Goodyear, was performing some chemical experiments with crude rubber extract from rubber trees. And for some unknown reason, he mixed sulfur with the rubber and found that when he heated it and it cooled, it formed a very tough, very strong form of rubber. He didn't realize it at the time, but what he was doing was causing a polymerization reaction with cross linkages between the polymer strands. And today, this is the reaction that is used to make automobile tires and many other polymer related products. The first synthetic polymer, it turns out, was nylon, first synthesized in 1930. So we're going back almost 100 years. Nylon is truly amazing. You can make it in any shape imaginable, any size, any thickness, any color, any texture. And during the same year, neoprene was invented at DuPont. And you're actually familiar with neoprene a little bit. You may not realize it, but if you take your garden hose and you're ready to hook it to your faucet, there's a little black rubber washer in there. That is a compound called neoprene. Very hard, very strong, very resistant to almost all chemicals. If we take the polymer chemistry just a little bit further, polyethylene was discovered in 1933, and Teflon was literally discovered by accident at the DuPont lab in 1938. This is polytetrafluoroethylene, high density polyethylene, 1953, and many other polymers have been developed since then. And think about everything in our lives that we touch contains polymers. Our computers, our cell phones, our cameras, jewel shopping bags, televisions, all kinds of packaging, laundry baskets, you name it, and it's got a polymer in it. Almost everything we use today. One last thing I want to cover is oxidation. You know, we humans consume starches and sugars. This is glucose. And our bodies burn this glucose by combining with oxygen to produce carbon dioxide and water. And all of the hydrocarbons that we burn, natural gas, propane, gasoline, all of those burn with oxygen. And again, they also form carbon dioxide and water. Now, you might be thinking that since the Industrial Revolution, we have been pouring millions and millions of tons of carbon dioxide every day into the atmosphere. And this has been going on for years and years, hundreds of years, a couple of hundred years. You might be thinking the Air should be saturated by now with carbon dioxide, and we should be asphyxiated. Why doesn't that happen? Why is the level of oxygen in the air sitting at 21% constantly? And this is out of one of the Chazdei Hashem, one of the gifts that Hashem has given to us, and that is trees. Billions and billions of trees. And what do trees do? They reverse that reaction. What happened here? The sugar combined with oxygen to form carbon dioxide and water. But look what trees do. Trees take carbon dioxide out of the air, react it with water, with the process that we know of as photosynthesis. It's catabolized by sunlight. And what happens? It produces sugars, which the plant uses, and we, of course, consume ultimately, and oxygen. And because there are so many trees producing so much oxygen every single day, the atmospheric oxygen concentration remains at this number of roughly 21%, literally, hopefully forever. We don't think too much about the composition of air. It's really not on our radar screen, but if air had a significantly different composition, we would probably not be here. Take a look at what our master chemist has done. These are the components of air: nitrogen, oxygen, and argon. Add those up, 99%. These are the more trace components in air. There's a quite long list here. And Hashem was kind enough to give us, if you look on the bottom here, 99% are harmless things: nitrogen, oxygen, argon. And of course, we can't live without oxygen, but all of the ones in this other list over here, not all of them, but many of them are really toxic. Methane is toxic. Ozone. Nitrogen dioxide reacts with water to form nitric acid. Iodine in large doses, carbon monoxide, ammonia. These are all toxins. But fortunately, Hashem made air so that how much is there? Millions of percent or hundreds of thousands of a percent, very, very tiny amounts. You know, the noble gases, which we used to call inert, they now make different molecules. And just think about this, about how important helium and argon. I mean, how could we celebrate somebody's birthday without helium balloons? And how long do you think an incandescent light bulb would last if it were filled with air? We probably aren't even aware of that, but the amount of air in an incandescent light bulb is zero. That volume has been backfilled with argon, because if there were any oxygen in that bulb, a filament would not last 5 minutes before it burned out. So just a few final words. Those are just a few of the hundreds and hundreds of examples of how chemistry impacts our daily life, how we are dependent on the miracles of Hashem every second of every day. And yes, we do take them for granted, all of us, but we have to be very aware of who is in charge. And as we say on all of our chagim, we give thanks to Hashem for keeping us alive. Thanks for your attention, and I'm going to take this off screen sharing, and I'll be very happy to answer any questions that you might have. Any questions from anyone? If not, then I want to share my screen again and show you what is coming up. The next STEM meeting will be 1 week from today at 12 noon. The speaker will be Rabbi Isaac Rice, who lives in New York, and his topic will be erasing the name of Hashem from a computer screen. Anytime that you want to know what the next topic is, simply go to the KINS website, and of course it will be posted there. And this is the schedule that is coming up from now through December 15th. You will note that I have moved Dr. Jonathan Green's talks back to December 8th and 15th to give him time to recover from COVID. Rabbi Aronin will be talking about Techeles, color and controversy. So we have some interesting topics coming up, and I encourage you to please feel free to join us for every one of these on the next few Tuesdays. If you have no questions, then I will end this conference and look forward to seeing you